A thread library is defined by an API, which is used for creating threads and then managing them, closing them, whatever. The thread libraries could be implemented in two different ways. You can implement the whole thread library in user space, or in some cases, the operating system also provides support for the library at the kernel level. We have two different strategies in designing and using threads. One is asynchronous threading, and the other one is synchronous threading. The default one is asynchronous threading. That means, remember, each program, even if you don't use multi-threading at all, each program at least has its main thread. That's where your main function is running. If you're using multi-threading, you create threads from that main thread. If you don't use multi-threading, then it will be your only thread that's running. So when the main thread creates, say, another thread, both threads will be running in parallel or concurrently, let me say, because it could depends on how many cores are assigned to that process. But the important thing is they could run in parallel if they have sufficient cores available. In other words, the main is not waiting for the other thread to complete. So it's not like a simple function call. Remember, in the case of a simple function call, like if you call printf from main function, it will wait for printf to complete and then main will continue. In this case, they're running in parallel. However, sometimes we would like the main thread to wait for the completion of the other thread. This would be typically required when the main thread has created the other thread to prepare some data for it to use. So the main cannot continue in that case. The next instruction cannot be executed before that data is prepared. In that case, the main wants to stop and wait for the completion of the other thread. We say the main is waiting for the other thread to join back to itself. Okay, so that second case is the synchronous threading. But as I said, by default, if the main thread does not try to wait for the other thread it has created, then the default case is the asynchronous operation of these threads. Now these, for the implementation of the thread libraries, there are three libraries that are popularly used. One is the Posix thread library, which is called pthreads. The second one is by Microsoft, the Windows thread library. And the third one is for Java, the Java threads library. Now for Posix pthreads, they are implemented in user level and kernel level. The Windows thread library is implemented in kernel level. And for the case of Java threads library allows the Java applications to create their own threads. But remember, everything in Java, the Java application itself, is running on a Java virtual machine. And generally, the Java virtual machine is running on top of the host operating system. It is possible, by the way, to have the Java virtual machine running directly on the hardware, but in general, as I said, it's running on top of some host operating system. So how the threads are really implemented depends on the Java virtual machine implementation and also on the host operating system itself. Anyways, we will first start with the discussion of the Posix threads, the P threads. As I said, the P threads are provided as either user level or kernel level. The standard is defined as by IEEE under the name IEEE 1003.1c API. Pay attention, this is an API just like any other library API, Applications Programmer Interface. This is just a specification, not the implementation. In other words, if you try to get this API from IEEE, what you will download will be a Word document. It will not be source code. The API is just a specification which defines the behavior of the library functions. It says you should have functions with these names. They should take such parameters. It should return such a value, and it expects this, it does this. That's what the API does. The implementation is something else. You should find it from somewhere else, either in source code or in binary. But what the API, what IEEE provides you as the API, as I said, is just a document. But pthreads is very common. It's used in Solaris, Linux, and even in Mac OS X. It's being used. So let's look at an example use of the Posix library for threads. Now, in this example, our aim is to get a number from command line. When you're running the program as a command line argument, you enter a number. Whatever that number is, this program will find the sum of all positive values from 1 to that number. Of course, by Gauss law, you could just calculate this as n times n minus 1 over 2, but let's, for the sake of the example, let's assume that we are just adding the values from 1 to that number 1 by 1. So that's what the thread is going to do. Of course, you could implement this without using threads simply in a program. This is a very, very simple task to do. But just for the sake of the example, let's assume that we don't want to do it in a single thread process, but we want to make use of multi-threading in this program. So we implement this functionality, this for loop actually, from 1 to that number we will call upper, in a for loop. So it's very simple. We initialize sum to 0, and upper is coming as a parameter, a command line argument. So it comes as a string. So we use the auto function, which stands for the alphanumeric to integer function, which will just convert the string to an integer value, and we just run the loop on that. So the runner function, as you see, is very simple, but a couple of things you need to pay attention is the function here is supposed to be a void pointer function. So it can return an address, but pointer to not something special. That's why we make it a void pointer, not integer or character pointer. And it takes a parameter, which is again a void pointer. And when you're completing this function, which is actually your thread, you should end it with the pthread exit function. This specifically tells C compiler that it is the end of this thread. Okay, so not return, but you use pthread exit here. On the main thread, what we do is actually we create a thread with this pthread create function here, and we call the pthread join here. So in other words, according to what we discussed earlier here, we're implementing here the synchronous threading idea. So we're going with this strategy. So we create a thread in the main thread and wait, which is, we create this thread actually, and we wait for it to complete. Okay, so what we give to pthread create function is the thread ID argument, the attributes, the function to be executed, and the arguments to be passed to that function. Okay. By the way, this runner function is in the same file with this one. It just didn't fit on the screen. That's why I've written it in a separate box. But this is altogether a single file. Okay, so it's just passing the pointer to function here as runner, the same name here. This is the argument to runner, so that's what param will become. The important things here are you need a thread ID because you need to keep track of your threads because you could be creating multiple threads. Don't forget what those thread IDs are, otherwise you cannot find them. And with each thread, you can have a set of attributes. We're going to discuss what those attributes could be later. But for the moment, some attributes. Now, what are those attributes? At the moment, I don't know what they are, but I'm going to take the default arguments, sorry, the default attributes. So with the pthread attribute init method, we're getting the default attributes in our system, whatever they are. For the moment, let's not deal with that, and use them as they are. So get it from the system, learn what attributes should be, because you're supposed to provide it when you call pthread. Okay. The type of attributes variable, attr variable here is pthread attribute type, and the type of your thread ID is pthread type. Okay. And here we call join. We're not joining anything actually. We're waiting the thread to join us. So this is the main thread. Main thread is waiting the thread to join us. Which thread? You should tell the thread ID. The thread ID is what was returned actually. See, this is a variable parameter. What was specified by the pthread create while the thread was being created. That thread ID is passed. And when we're done, we can print sum. Pay attention, the sum variable is defined as a global variable. It's outside the main function. It's a global variable. Therefore, the runner function also can access this global variable. And actually, what's being done is runner function, while it is running in parallel, it's modifying that sum variable. We have waited for the thread to complete. So while the thread was running, of course, some would have different values and it would be continuously changing in each iteration of this for loop here. But since we have waited all the way for the thread to complete before calling printf here, we're sure that sum has the ultimate value in it. Okay. Now, I will show you a more detailed example based on this example, but I've written for you a more detailed example. I will go over that, but before going on to that, let me just look at another example, which is quite simple. Then I will go to that more complex example. And that simple example is this one. It's not even a complete code. In the previous one, we just created one thread. What if you want to create more threads? You can create as many threads as you wish. Okay, and if you want to synchronize with all of these threads, you should call join for those threads one by one. it's not possible to say, okay, return me, I will wait for all threads to complete. You should say, I want this thread to join me, I want the other thread to join me, the other one, the other one. You have to tell it one by one. That's why we have a for loop here for that. And that's also why you should be keeping track of the thread IDs. That's why we have an array here to keep the thread IDs. Anyways, now let's look at that more complex example. Okay, actually there are two. I've written two pieces of code based on what we have done here, the example there. So let me start with the first one. What I'm doing here is, as I said, it's based on the previous one, but it's different. What I want to do is, this time I'm creating two threads. So there's also the main thread. So in total there are three threads. So the main method is creating two threads, and these two threads, each one is doing something slightly different. Okay, they're both calling the runner function, but depending on this argument, which is, for the first one, order 1 is true and order 2 is false. So I'm sending order 1 to the first thread and order 2 to the second thread. So I'm creating both of them with pthread create. So this is the difference between them. And if you look at the runner method, the runner method takes this value into a local variable named first in a loop that starts from 2 all the way to 6, including 6. That means 5 times. It's looking at first if it's the first process, sorry, the first thread, not process. If it's the first thread, it's multiplying value by the value of I. If it's sorry, if it's the second thread, in that case, it's doing an addition. It's just incrementing by 2. Okay? And also, it is in each iteration of this for loop, it's displaying a mark on the screen. If it's running as the first thread, it's displaying a dot. And if it's running as the second thread, it's displaying a star. Okay? We're working on value, which is initialized as 100 up in here. So what I do is the following. I define a global variable named value, initialize it to 100. I define two variables, order 1 and 2, so that I can differentiate between the first and the second threads according to this variable. I initialize the attribute. I get the attribute, default attributes from the system, and I create two threads with these attributes. To the first one, I pass the value true. To the second one, I pass the value false. And then in the main thread, what I do is the following actually. I'm just in a loop 20 times. I'm displaying the value of the variable value on the screen, saying main colon value equals whatever its value is. Okay? Now, in the code, by the way, the code is available both on Moodle and also on YouTube. In the code, you will see comments like to do. These are things that are to be done, because while running this code, I will be applying these to-dos one by one according to the number here in this order. Okay, so for the moment, let me just compile and run this program. To compile and run this program, I need to, I'm using the GCC compiler. I'm compiling thread example1.c program. I will name the executable thread example1. I'm going to run this over and over so to guarantee that I've successfully compiled and I'm not by mistake running the previously compiled version. Before compiling, I'm just removing the previous binary, if any. Of course, instead of this, I should have written a makefile, but I was too lazy to do that. And then I run the program example1. Okay, so that's how I'm running it. Actually, I'm removing, if there is any previously compiled binary, remove the binary, compile from scratch, and run the binary. Okay, so let's do it. Oops, it went too fast. Okay, as you can see, 20 times in the loop here, 20 times I have displayed the value of main. It was, remember, initialized to 100. It is still 100. Now, what does that mean? It looks like my threads didn't run at all. Remember, one of the threads multiplies value by I and the other one increments by 2. None of these have run because it's still 100. Let me try that once again. As you can see, it's always 100. Why is this happening? Actually, is there a bug somewhere because my threads are not running? Actually, my threads are running. The problem is actually the following. The main thread creates the other threads, the two threads, but the main thread is also running. So before the other threads do anything, in this case, my main thread was running so fast that the main thread completed and came to an end. The main thread completed where? Here. The main thread run the for loop, just 20 times, displayed something on the screen, that's all. And then said main thread is executing with value something. Yeah, it did. And that value is 100, as you can see. And when the main thread ends, all the threads created by main, actually all threads in that program, have also ended. So yes, the threads were created, but they didn't get the chance to execute because the main thread was too fast. It was not waiting for them. Okay, so let's do the first to do. The first to do here says uncomment the sleep call below. So I'm just going to open this sleep statement, remove the comment there, and compile and run once again. Now it's going slowly, and now you see the main method is displaying the values, but meanwhile you can see this plus and dot, sometimes plus dot, sometimes dot plus, sometimes only dot, or sometimes only plus. So I have all of them. And also, now remember the plus, let's go back to the code. The plus was displayed when first is false, which means the plus is displayed by the second thread and the dot is displayed by the first thread, and each one is executed 5 times. So I have executed the first thread, look at the dots, once, twice, this is the third time, fourth time, fifth time, and the first thread has completed. So the first thread says here, first thread exiting. This string here is either first or second, depending on the Boolean value first. And if it's first, I put a single tab. If it's second, I put double tab so that they're not completely aligned. I can see them easier. Okay, so the first thread is exiting here. Second does not exit yet because it has been executed once, twice, and 3 times here. When it executes twice more, it will have executed 5 times, and will say second thread is exiting. So once the first and the second threads have exited, the value of sum has reached its final value. That's why it's not changing anymore. The main thread still keeps on printing on the screen, but it's always the same value. It's 73,696. It's fixed there because there are no threads left to modify the value of sum. If I run the program once again, oops, things are different now. See, it was 100, then 204. Things are running differently, and it ended up with a different value, as you can see. The ultimate value was 73,696. Now it is 72,976. It's quite different. And the reason is the order of execution of the first and second threads is different here. I didn't change the code, pay attention. I just ran the program once again. Depending on which order these threads are running, the output is changing. This is actually the most important point in this example. We have 2 threads that are competing with each other for the same variable. If what the threads were doing was the same thing, like incrementing by 1, it wouldn't matter which one comes before or after the other. But here, one of them is incrementing by 2, the other one is multiplying by I. So if the order changes, the result also changes. That means actually, at the moment, my program is not stable. Depending on the order of execution of the threads, I get different results. If I run it yet once again, it's again like the second one. But every time you run, you could get a different value depending on the different combinations. You can get all different possible combinations. Now you might ask, I'm not changing the code. Why is it running differently? Well, it depends completely on scheduling. And see, even if I don't change the code, the scheduling decisions might be different because this is not the only program running on my computer system at the moment. So the scheduler just makes a decision according to the conditions at that very moment. And since different things are happening on my computer, it could be scheduling in a different manner. And that scheduling, unfortunately, affects the behavior of my program, which is not nice, by the way. Normally, we don't want something like this. Anyways, this was with to do 1. Now let's go to do 2. What does it say? It says comment the call to sleep 1 in to do 1. Okay, so let's do it. So remove the sleep and uncomment the printf and pthread join functions below. Okay. Let's uncomment these. Now let's see what we did. Now in this for loop, we're not waiting anymore. We're just going fast. But what we have done here is printf just says main thread is waiting for the threads to join, and really it does that. Okay, so it's waiting for the threads to complete. Now let's save this and compile and run. Since we are not sleeping anymore, it wrote the values of main very fast. When it started printing the values after 200, it seems like thread 2 had a chance to execute. Sorry, thread 1. I'm sorry, that's 1, the dot. But then main was running so fast that the threads did not have a chance to execute. Main completed. Okay. Main almost completed actually. Main didn't come to the end because when main came here, it just said main thread waiting for the threads to join, and it will wait for thread 1 to complete. Main cannot continue until thread 1 completes. When thread 1 completes, it will also wait for thread 2 to complete. Now, maybe thread 2 had already completed. If so, it will immediately continue. If not, it will keep on waiting until thread 2 completes. But you will come to this printf statement if and only if both thread 1 and thread 2 have joined the main thread. And that's when the main thread exits. Now let's see. Yes, although it was like 200, then 202, suddenly it jumped to 72,000. Because remember, it was waiting here. Okay, let's run it once again. I don't know if the output will be different or not. It could be anything. The output value happened to be the same here. Just running it for the third time. Really depends. Okay, see, this time it's different. Different than this one. Okay. Now, let's continue with the third to do. It says, make sure sleep 1 in to do 1 is again uncommented. Okay, so let's uncomment it. Change the sleep duration below for first and second threads from 1 and 2 to 3 and 2. That means, come here, see. This is the run method. The run method, in the for loop, after each modification, it waits either for 1 second or 2 seconds. For the case of first thread, it was waiting for 1, and for the case of 2, it was waiting for 2 seconds. Now it says, let the first one wait longer, make it 3. That's what my comment says. Okay? So let's compile and run once again. Now the first method, the first thread is waiting for 3 seconds, and second one is waiting for 2 seconds. Since first is waiting longer, this time second completes before the first one. See, in the previous ones, it was always the first completing earlier because the first was waiting shorter. This time, second is waiting shorter. That's why the second is completed first. So see, the value of the variable is completely different now. Oops, sorry. So let's go to Ch4, if I can find it. Ch4 says, what would happen if we used a single variable instead of order 1 and order 2? What it means is the following. Let's, for example, define here just a variable named, order, initialized to, let's say, true, or why did I do it like this? Okay, let me go this way and send order. Okay, then say order becomes false and send order. Okay, so order 1 and order 2 are not used. That's not important. If you want, I can also comment that I'm not using order 1 and 2 anymore. I just use the same variable. I've defined a new variable named order. It's initially true, so for the first one, again I sent true, and for the second one, I sent false. Would this work? Rather than having two separate variables, order 1 and order 2, and sending these as parameters to the threads, I have used the same variable. I just want to save from the memory space. Why do I define two variables? Let's just work with one variable. It sounds like logical, right? So you wouldn't expect any difference. Of course, from the way I'm talking, you understand that there's something different here. And you will see what now. Actually, I made this mistake in the beginning while I was writing the code. And you will see what that mistake was. Now I'm running the code. I've just changed that variable. I just see pluses. Still pluses. I don't see any dots. And see, second thread exited twice. There's no first thread around. That's why I didn't see any dots. It was always the second thread running. And interesting enough, second thread is created twice. Actually, it is two threads are still created. There's still TID1 and TID2. There are two threads created. But remember, I was deciding whether it was thread 1 or 2. I was deciding on the action based on the argument here, which was true for the first one and false for the second one. However, I made the following mistake. First, I made it true. And I created a thread, TID1, and said, okay, use this variable order. Okay? Before it did anything, before it had the opportunity to do anything, in the main method, I have modified order this time to false. And I create the second thread and I pass the argument false to the second thread. So from the point of view of the second thread, it will try to access the variable order and its value is false. So it will say, yes, I'm the second thread. That's fine. So really TID2 is second thread. There's no problem there. However, now TID1 starts running and it wants to look at the argument which is the address of order. And when it goes there, what does it find? It cannot find true. Although it was true at the time I created TED1, by the time TED1 had the opportunity to look at what its parameter was, main modified it to false. So TED1 thinks it's also the second thread. That's why in the output you see second thread existing twice, and that's also why you don't see any dots but only plus signs here. And that's why nothing gets multiplied. It's just added. Starting from 100, 5 times TED1 adds 2 on that, and 5 times TED2 adds 2 on that. So in total, 10 times 2 is added to 100. So you get 120, which is the value of the main value of the variable when main completes. So that's again something you should be careful with. Actually, as I said, I made this mistake myself. So just to show you the possible error. So let me correct it once again. This is the correct execution. So if I search for to-dos, this is 1, 2, 3, and 4. So we're all done with the to-dos. Okay. So let me look at the other example now. The other example is similar. Again, I initialize value to 0. I create 2 threads, again true and false. I print the value. This time I have sleep set. And this time the main thread immediately exits. Okay, after displaying these values, it exits. And if you look at the runner code, in the case of runner, it will again do these multiplication or addition, and in each case it will just wait for 2 seconds, and the runners also complete. Now note that this time the loop on K is running 4 times, not 20 times. It's running 4 times, and in each iteration it's just waiting, sleeping for 1 second, so it will complete in 4 seconds approximately and terminate much before the runners, because each runner waits for 2 seconds and runs for 5 times. So each runner executes for 10 seconds and the main thread executes for 4 seconds. There's some plus on that, but you can ignore that. Okay, so it's obvious that the main thread will complete before the other threads it has created. So normally you would expect the main thread, when the main thread ends, you would expect it to also kill the other threads. And let's see if it works that way. I just modified them to example 2. See, they are running. Main has completed. Oops. The other 2 threads continued. They did not terminate as it did in the previous case. And the reason is the following. What I have done different here is these two lines. Actually, one is comment, so it's this one. In Posix pthreads library, you can use the pthread detach function to detach this thread from the main thread so that it doesn't get killed when the main thread completes. So both of these threads, TID1 and TID2, will detach themselves by calling pthread self. It gets its own thread ID, and by specifying its thread ID, it's able to detach itself from the main thread. And there's one other thing I did, and that's this pthread exit. See, if I just, as the comment, as a to-do comment says, if I just modify this, see, if I don't use pthread exit here in the main thread, when the main function ends, you know, the whole program ends. So that was the case also with the first example. In the first example, when the main thread ended, the whole program was completed. Even if there were running threads, they would be killed, and the whole program terminates when main ends. This time, for main, we didn't use return. Even if you don't write return here, by default, the default of ending of the main function is actually returning a value. By default, it will be returning 0. So if I don't say pthread exit, main thread will not exit like a thread, but it will just do a regular return from main, which implies the end of life for that program. Therefore, the threads will be killed. But once again, if I let the main thread exit like other threads by calling pthread exit rather than return or exit, and if the other threads have detached themselves from the main thread, they will survive. And once again, that's what happens here. The main thread terminates when value is equal to 618, but the other two threads continue running, and finally they will complete.